So welcome everyone to today's seminar. This is the second last seminar on our cycle of seminars this semester, where we're celebrating the 150 years of the School of Engineering, and also we had, for this reason, we chose a number of international speakers, and I'm sure you enjoy today's seminar. Before I pass on to Lucia, who will introduce our speaker, I just want to mention that our enrollment for the postgraduate studies, both in materials engineering and nanotechnology and electroengineering and computing is open, right? So if you want to seek further studies in MSc or PhD degree, please check our webpage. So now I pass on to Lucia Saito, who's going to introduce our speaker.
Good afternoon, everyone. Thank you, Cristiano, for the beginning of this seminar. It's a pleasure to receive Professor Zhipei Sun from Aalto University. He will present on the topic 2D materials integrated nonlinear photonics. Zhipei Sun is a professor of photonics and the head of the Photonics Research Group at the Department of Electronics and Nanoengineering of Aalto University in Finland. He earned his PhD from Institute of Physics, Chinese Academy of Sciences in 2005. He is currently actively involved with European Research Council Advanced Grant, European Quantum Flagship, Academy of Finland Photonics Flagship, and Academy of Finland Center of Excellence on Quantum Technology. His research interests include nonlinear optics, nanophotonics, and ultrafast photonics. He mainly focuses on carbon nanotubes, graphene, and other two-dimensional layered materials for photonics and optoelectronics. Thank you for your attention for our invite. The time and the audience is yours.
Thank you, Lucia, for the very nice introduction. Also, thanks for the invitation. It's my great honor to give a talk here. Also, thanks to the organizers to put this wonderful seminar during this pandemic situation. Before the talk, I would like to send my congratulations to your 125th anniversary. I still remember the wonderful time I spent in Brazil around 4 years ago when I attended the NT17 conference in 2017. I really enjoyed the trip to Brazil, where I met Professor Toro and also Professor Cristiana de Matos, and also their group members. So from the group picture, you can see the Cristiano doesn't change too much. And here I am. So I really hope we can get back to the normal situation and we could meet together in person. Not at the moment, the EU is open for traveling. So it seems that we are not very far away to go back to their normal life. Okay, let's go back to the science. Today, I will talk about the nonlinear optics. Nonlinear optics has been widely used for our everyday life. For example, here, the nonlinear optics changes the wavelength of the laser from the infrared to the green wavelength for the green laser point. And also you can use nonlinear optics for the high-speed data communications and the generation of the photon pairs for the quantum technologies. However, nowadays, the nonlinear optics is based on the bulk crystal, which will make the system quite complicated. Here, just to give you two examples. If you go to most of the traditional photonics lab, you will find this is what they typically have in the lab. They have a large number of the bulk components to generate, manipulate, and also detect the photons. This is a similar case if you, for example, open the door of your internet connection rooms, you will find something similar in our this commercialized photonics products. This is really great challenge for the current photonics technology. So the motivation of my research is to integrate all the different components in a very tiny chip and to address the grand challenge of the current photonics. To start with the integration for nonlinear optics, let's go back to the fundamentals of the nonlinear optics. The conversion efficiency of the nonlinear optics, which can be simplified by this equation. The conversion is normally decided by the nonlinear optical response of the crystals you used instead of your measurements, and also decided by how much peak power you put on the nonlinear materials. Also can be it's decided by the light matter interaction length. If we have a very good phase matching conditions. To improve the efficiency, people is very familiar with use the lens to focus the light to increase the light power. Also, you can put your your nonlinear crystal inside of a cavity to introduce the resonance to enhance the light matter interaction. Also, to increase the length, people have invented this photonic crystal fibers to significantly enhance the light matter interaction length to improve the this nonlinear conversion efficiency. For example, for the super continuous generation and also the frequency comp. The motivation of my research is to use a one-dimensional and two-dimensional nanomaterials with a very large nonlinear response, and then use them to combine with the different micro and nanostructures to fabricate efficient on-chip hybrid devices with these nanomaterials. This is the outline of my talk. First, I will introduce you our recent work about the transition metal dichalcogenides based nonlinear devices. After, I will discuss the enhancement and also integration strategies to improve the nonlinear conversion efficiency. After, I will introduce you what we are planning to do in the near future. Nowadays, graphene is a very popular material, which is very interesting for physics, chemistry, and also for the biotechnology, mainly due to many interesting properties. Here, I will not go to the details. Just here, I want to mention you that the major performance advantage of using graphene for photonics is because of the graphene can operate in a very broad operation bandwidth. This is because of the linear bandgap structure of the graphene. So for example, you always have the resonance, the light absorption from the visible range to the infrared range, or also even to the terahertz or microwave range. On the other hand, this means the graphene will introduce the optical attenuation at a very broad operation wavelength range. This could be bring some disadvantage for the graphene-based photonics. Nevertheless, thanks to the development of the graphene fabrication technology, nowadays we could be able to fabricate thousands of the graphene devices on one wafer. This is our demonstration of the graphene-based photonic devices. You can see we could be able to fabricate more than 1,000 modules on one 4-inch wafer. Here, give you a picture about how our graphene device look like. This is the bottom context, and this is the top context. And our graphene devices is around 12 microns, which is fully compatible with fibers and also optical fibers and silicon integration devices. Graphene also have been well studied for nonlinear optics. Here, just to give you a few examples. The most hot topic is use graphene for cerebral absorbers and ultrafast lasers. Some of you might be very familiar with this topic, as I have been reading a lot of wonderful papers from your university. For example, papers from Lucia, Cristiano, and also from Del Toro. Graphene also have been used for optical limiting, which is a reversed process of the cerebral absorption. Full-width mixing also has been demonstrated with graphene. Nowadays, even people can use the full-width mixing instead of graphene for that very high-speed optical switch up to 10 gigabit per second. Third harmonic generation has also been demonstrated a few years ago, including results from my university, and also high harmonic generation also have been demonstrated a few years ago in graphene. But if you want to use the graphene for second order nonlinear process, for example, here to generate the frequency, which has 2 times larger than the input frequency, this process is called second harmonic generation, which is the process you used for the laser point. This process is also the most useful nonlinear process for the applications. But if you want to use the graphene for this process, you will get really disappointed because the graphene doesn't have the second order nonlinear response because of graphene has the central symmetric structure, which doesn't give the second order nonlinear response. However, people have tried to use a different symmetric breaking method, for example, to use the interface or twisting or use a defect. You could be able to introduce the second order nonlinear response. If you are interested, you can go to our recent paper. Anyway, if we look at the other 2D materials beyond graphene, for example, this MOS2 here, this shows the atomic structure of the monolayer MOS2. As we know that the true edge phase of the MOS2 has a central symmetric breaking structure. You can see from here. And also another advantage of using MOS2 is the MOS2 has this unique direct band gap structure. When you have the monolayers, when the thickness of when the thickness goes to the monolayer. So that means you can have a certain transparency windows for the near infrared light input, so you could be able to get much high efficient nonlinear response. Here we tried MOS2 beyond the graphene. We fabricate the devices with the most famous mechanical exfoliation method. We started with a very thick bulk crystal, and then we fold the tape and then express them, and then we fold them again, and then we just unfold them again. Then we would be able to get the monolayer materials, for example, showing here. This is a zoomed picture about the flake we get. You can see here we could be able to get the monolayer MOS2 here. This is a bilayer area, and also this is a small part here is also monolayer. This is a tri-layer, and this is a little bit more thick layer samples. First, we tried a second harmonic generation. As we already discussed in this process, the 2 input photons will be converted into 1 photon with a wavelength half of the input wavelength. So we call this nonlinear process as the second harmonic generation. The input wavelength we tried in our measurements is 1560. So the generated light wavelength is half of this number, around 780 nanometer. This is our flake. And this is our second harmonic generation image results we get. You can see here, we could be able to get very high second harmonic generation with the monolayer, and also monolayer here. With the trilayer, we also can get second harmonic generation. But something very surprising for the bilayer here, for the bilayer and also for the thick layer here, we couldn't be able to get the second harmonic generation. The reason behind is because of for the bilayer and also for the thick layer, they have a central symmetric structure, which doesn't have the second order nonlinear response similar to the monolayer graphene. We also try to measure the third harmonic generation. Here, the 3 photons will be converted into 1 photon with the frequency 3 times larger than the input pump frequency. We used the same flake, and this is the third harmonic generation results. You can see here, we could still be able to get the third harmonic generation with the monolayer samples, but with a little bit of a weaker signal. And you can see here the third harmonic generation signal increases with the sample thickness. So this is pretty expected. I also want to mention here, similar results also have been reported by Professor Cristiano D'Amato's group. If you go to the nonlinear optics textbook, we will find that the conversion efficiency of the nonlinear process normally decreases with the order. So that means the third harmonic generation is always weaker than the second harmonic generation. But from the results we get here, you can see we get completely different results. Here, what we get is the third harmonic generation efficiency is around 30 times larger than the second harmonic generation. So this is the very big surprise for us. So to fully understand this, we did the third harmonic generation as a function of the wavelengths, as a function of the third harmonic generation wavelengths. And then we extract the chi3 of the MS2 at the different wavelengths. We could easily find this 7 resonance peaks with a much larger third harmonic generation efficiency. To fully understand this, we compare these results with the second order differential reflection spectrum, linear reflection spectrum. We can clearly see that all those peaks are corresponding to the different excitonic resonance states inside of MS2. If we continue to increase the pump power without damaging the sample, you could be able to observe a much higher order harmonic generation process. For example, fourth harmonic generation. This is the results we get. This is the spectrum of the output spectrum. Here you can see this peak is due to the second harmonic generation. This is the third harmonic generation, and this is the fourth harmonic generation. You can see here also something very strange. The fourth harmonic generation also is pretty comparable to the second harmonic generation. At the moment, we still don't understand the reason why. We are still trying to work with theoretical scientists to understand why here the fourth harmonic generation, which is typically very weak, but here the fourth harmonic generation is very strong compared to the second harmonic generation. Anyway, because of we use the pump wavelengths around 15-16 nanometer, so much higher order harmonic generation is in the UV range and not observed. This is because of the strong absorption inside of the MS2 in this wavelength range. This indicates if you use a much longer excitation wavelengths, then high harmonic generation could be possible. You can see here, if we tune in the pump wavelength from 1550 nanometer to 2500 nanometer, we could easily observe the fourth harmonic and also the fifth harmonic generation from the monolayer sample. This is also has been reported by the Rios group in US. We also tried the parametric generation with the monolayer MOS2. This parametric generation process is the most common way to generate the light at a new frequency. This figure shows what we get with the monolayer MOS2 device. You can see here we could be able to generate the tunable pulses across a broad spectrum range from 1550 nanometer to around 600 nanometer. This tuning range is mainly limited by our pump laser source. It's not limited by our monolayer materials instead of the experimental setup. Currently, we know that there are many new 2D materials that have been discovered almost every day. This is really fantastic for the researchers, in particular for the younger researchers. You always can find something new with different new materials. On the other hand, this is also very challenging because we want to select the best materials for the measurement. So this is really challenging. So we are asking ourselves, so which 2D materials are better for nonlinear optics? To answer these questions, we went to the literature reviewing and then compare the nonlinear optical results published by the different groups. Then we found it has a huge problems. For example, the Chi2 of the MOS2 at 800 nanometer. The reported Chi2 can have a 3 order of magnetic difference if you compare the results from the different groups. The difference is quite understandable because of different groups use different lasers with different pulse duration and use different focus conditions and even use different calculation equations. So this is make the comparison of the 2D materials very complicated. To answer these very fundamental questions, which 2D materials is better for nonlinear optics, we carry out a very easy but very time-consuming measurements by transfer the different 2D materials on one substrate and then compare them at the same time in a pretty fair way. So in this way, we could be able to, in this way, we don't have any problems like what we mentioned, for example, the substrate contribution and also doping and also different focus conditions. At the beginning, the measurements, we worked on this just for our own information, but then we found what we get is really surprising. Like all the measurement before we did a very simple, before we do the measurements, we did a very simple theoretical estimation. We all know that the most of the, as we know that the nonlinear optical response of the materials normally is highly linked with the electrical band gap structure. So if we compare the electrical band gap structure of the MOS2 and the WS2, which have a pretty similar band gap structure, then we can easily, get to the conclusion that this MOS2 and the WS2, they should have a pretty similar nonlinear response. And also similar response should be expected from these two materials. But then the results, what we get is completely different from what we estimated before the measurements. Here you can see that with MOSE2, we get a much stronger nonlinear response. And with WS2 and also WSE2, we get a pretty comparable nonlinear response. Surprisingly, with MOS2, we get a very low conversion efficiency. To fully understand the physics behind the process, we've been working with theoretical people from ICFO. We found that the reason why the MOSE2 has much stronger resonance, has much stronger conversion efficiency, because of the exciton of the MOS2 its resonance to the half wavelength of to its resonance to the second harmonic generation wavelength around 780 nanometer. And the reason why WS2 and WSE2 they have a pretty similar response is because of they have a pretty similar intraband structures instead of the electrical band gap structure. At the moment, we still don't quite understand why MOS2 has a very weak response, around 10 times less than other 2D materials. At the moment, we are still trying to figure out what is the physics behind the process. So far, you can see we only compared 4 materials. As we discussed, there are thousands of new opportunities and different 2D materials. And also I've mentioned, we have a lot of different nonlinear process, second harmonic generation, for example, third harmonic generation, and also parametric amplification process and high harmonic generation. This will make the this nonlinear optics with the 2D materials very, very complicated. So for future research, what I'm thinking, we really need to work together between the experimental and the theoretical researchers to find out what is the most suitable 2D materials with the best nonlinear response for the different applications. Before I went to the integrated photonics that we are currently working on, we have already used the nonlinear optics inside of the 2D materials for the characterization of the 2D materials. For example, if we go back to the second harmonic generation of the MOS2, the polarized second harmonic generation response of the MOS2 is patent. This is due to the crystal symmetric of the MOS2. Therefore, use the second harmonic generation, you can estimate the crystal orientation of the flakes. Here, I would like to show you one video. So here, I would like to show you one video we take from these polarized measurements. You can clearly identify the different crystal orientations inside of one CVD flake. At the moment, this is very useful to look at the flakes. For example, if you want to make the different heterostructures with the different crystal orientations. And in particular, at the moment, the researchers are really motivated to twist the different 2D materials together to form these heterostructures with magic angle. At the moment, the second harmonic generation is one of the most effective way to measure the twist angle inside of the these heterostructures. Second harmonic generation also can be used to measure the different phases of the flake grown by the CVD method. This is the results. For example, you can see here, you can clearly see that this is the monolayer flake. This is the monolayer green, and this is the bilayer green. You can see here, we didn't see the strong second harmonic generation because, as I mentioned, the bilayer MOS2 has central symmetric structure, doesn't give you the second harmonic generation. So with this method, you can clearly tell the different phases inside of the flakes made by the different made by the different deposition method. We also know that the Raman and the photoluminescence can be used to check the green and green boundaries. For example, Raman and photoluminescence. But however, the Raman and the photoluminescence typically need a very, very long time because you need to check the whole response spectrum. For example, for one Raman image around Raman image of the sample around 4,200 micrometers squares, the time we need in our lab is around 7,000 seconds. But here with the second harmonic generation and third harmonic generation, is much, much faster because of you don't need to measure the whole spectrum. For example, for much, much larger sample, the measurement time for look at the samples is around 20 seconds. Here, I would like to show you the picture. Here you can see the results, what we did with the second Hammer generation and third Hammer generation image for the very fast and large sample, for the very large sample characterizations. We also worked with the black phosphorus, which has a very strong anisotropic response. We checked the third Hammer generation of the black phosphorus. For example, this is a flake we get from the Northwestern University. And we found that when the input light polarization is along the armature direction, along this armature direction, we get a much, much stronger third Hammer generation. But we changed the light polarization along the zigzag direction. The third Hammer generation is much, much weaker. Here, I also mentioned that similar results also have been reported by the Cristiano with the different inside of the black phosphorus with different thickness. But as I mentioned, because of this anisotropic response of the black phosphorus with the polarization of the incident light, so we could be able to use the third Hammer generation to measure the crystal orientation of the exfoliated black phosphorus flake. So this is our results. Then if you look at a little bit more details, then you will find something very, very interesting. For example, if you look at all these crystal orientations of the different flakes, you can easily see that. So those two flakes are produced at the same time when we do the mechanical exfoliation. And those different flakes are produced at the same time when you do the exfoliation. So this is something really interesting. You can use this third Hammer generation not only look at the crystal orientation, but also can tell so how many flakes are produced at the same time when you do the mechanical exfoliation. Again, here I would like to highlight the fast and the large scale characterization advantages of the third Hammer generation. For example, we could be able to measure the sample with around 5 to 5 millimeter square samples. We only be able to take around 2 hours. We could be able to fully characterize the thickness and also the crystal orientations of the flakes instead of the during the experimental measurements. So this is really quick for the for our research. At the moment, many people also is discussing about how to use green engineering and to use this green engineering to change the optical and also electrical properties of the 2D materials. Here we are working with Professor Liu from Peking University. We demonstrated that second Hammer generation can be very useful to measure the string vectors. For example, here, this is a CVD flake we used. We applied the string along the armature direction. Then we measure the second Hammer generation response as a function of the string. You can clearly see here, we could be able to detect the string applied the string directions and also the amplitude of the string instead of the flake. This is at the moment this is not possible with the traditional optical method. For example, with Raman and PL, we could only be able to tell the string amplitude, but you couldn't be able to tell what is the string directions. So the physics behind this process is because when you apply the string along the different directions of the 2D materials, the string will modify the nonlinear response by the photoelastic effect. So use this effect, we could be able to measure all this string, not only the string directions, also the string amplitude. As we discussed at the beginning, so we would like to integrate the current 2D materials with different silicon devices or fiber devices for different applications. On the other hand, I would like to highlight that although the nonlinear response of the 2D materials is very, very high, if you think about the thickness, it's very, very thin. But however, the absolute the value of the conversion efficiency inside of the monolayer 2D materials is very, very weak. This is mainly because of the very thin light matter interaction thickness. So for example, the conversion efficiency of the monolayer 2D materials is around 10 to orders of the -9. So this is a very, very low, which is not possible for the applications. So that means to bring the 2D materials for the applications, we really need to improve the light matter interactions by using the different integration method. Here, I'll give you a few examples about what we tried. This is the example we tried with to use the plasmonics, which has a very strong light confinement to improve the light matter interactions. So here, this is the different plasmonics bow tie these nano antennas to improve. We fabricate the different the bow tie nano antennas on the top of the MS2 monolayers, and then we look at the nonlinear response. For example, you can see here the pure bow type structure, the 4-wave mixing signal, and also the pure monolayer MS2 devices. The 4-wave mixing signal is very weak, but when you combine this bow type antenna structure on the MS2 devices, you will get around 10 times enhancement. We also demonstrate the broadband enhancement with plasmonics. So people maybe think about this is impossible with plasmonic structure, because from traditional people always thinking the plasmonics resonance is always very sharp. It's not possible to get the broadband enhancement with the plasmonics. So here we used a very smart strategy. What we did here is we fix the pump frequency, and then we change the idler frequency to generate the tunable 4-wave mixing signal. You can see here, because we fix the pump wavelength, and we fix this pump wavelength, which is always a resonance to the plasmonic resonance of the nano antenna. That means the 4-wave mixing signal will always be enhanced, because of the pump is always resonance with the plasmonics wavelengths. You can see this is our broadband enhancement measurement results without the plasmonics resonance. The 4-wave mixing signal is very weak. After the plasmonics enhancement, we could be able to get a broadband tunable enhancement covering from around 600 nanometer to 750 nanometer, which is pretty broad, covering all the major visible wavelength regimes. Large peak here is around 650 nanometer. This is because of we have the exciton resonance instead of the MS2. And the large peak around 750 nanometer. This is because of the emission wavelength is also close to the plasmon resonance. So we will get a little bit more higher emission at this longer wavelengths. As we discussed at the beginning, the absolute value of the light matter interaction strength inside of the 2D materials is very weak. This is mainly because of the very thin light matter interaction thickness. So you might thinking the most easy way to do that is to use the reverse mode interaction by integrating the 2D materials with different waveguides. This is what we tried to integrate the 2D materials with the fibers to improve the light matter interaction. For example, here, Professor Kai-Hui Liu's group in China, he has demonstrated to be able to grow, to be able to deposit the graphene inside of the photonic crystal fiber. Then we work together to use these hybrid fibers for the optical modulators with a very large modulation depth up to 20 dB per centimeter. You can see the light matter interaction is much largely enhanced if you compare to the absorption of the monolayer graphene, which is only 2.3%. For nonlinear optics, the group also demonstrated to grow the MS2 inside of the photonic crystal fibers. This is their growth strategy. And this is how the S-grown, the photonic crystal fiber look like. You can see which is very uniform. This is very, very suitable for the nonlinear optics because the uniformity will give us much less scattering loss. Here you will find the second Harmonic generation and third Harmonic generation results. With the bare, this photonic crystal fiber, we didn't see any second Harmonic generation. This is because of the silica doesn't have the second order nonlinear response. And if you compare the MS2 inside of the photonic crystal fiber results with the directly MS2 on the silica substrate for the structure like what we showing here, if you compare these two strategies, you will find that we could be able to get around more than 300 times enhancement with this second harmonic and nonlinear response. We also integrated 2D materials on the for the on-chip nonlinear optics. To realize the devices like this, we have developed this deterministic transfer technology for the 2D materials. This is the 2D materials transferred on the top of the waveguide. From the Raman image here, you can clearly see that the flake is transferred on the waveguide, and the overlapping area between the flake and the waveguide is around 15 microns. After device fabrication, we input femtosecond pulses from the left end, and then we measure the spectrum from the right end. From the picture, you can clearly see that the color change. This is because of we have the super continuous generation process happening inside of the this waveguide. We measured the spectrum. The black one is the input spectrum. The blue one is the spectrum without the 2D materials transferred on the top of the waveguide, and the red curve is the results after we transfer after transferring the 2D materials on top of the waveguide. You can clearly see that after with the integration of the 2D materials on the top of the waveguide, we could be able to get a much broader spectrum. This is because of the 2D materials could enhance the nonlinear coefficient of the silicon nitride waveguide. We have just discussed the different conventional methods such as resonance cavity, optical fibers, and waveguides to improve the nonlinear optical response. Those are pretty traditional way to improve the nonlinear response. Here we also have been working on the different unconventional approaches to improve the light and matter interactions. For example, I have already discussed the extonic effect, which is a binded electron and hole pairs. This can be used to enhance the nonlinear response of the second harmonic generation and also third harmonic generation. So here we take this extonic enhancement, and we demonstrate the electrical tunable four-wave mixing inside of the MS2 with this external resonance. This is our typical MS2 transistor structure. We have the input light at λ1 and input light at λ2. Then we look at the generated wavelengths by this four-wave mixing process. This is the results. You can see here the full wave-making response can be fully tunable by the electrical gating. So the reason behind it is because when we increase the gate voltage, the doping of the flake will change the oscillation strength of the exciton. Therefore, we could be able to tune in the nonlinear optical response instead of the MOS2. We also demonstrate the electrical tunable sum frequency generation instead of the MOS2 in the same devices, as long as the input of the generated wavelength is resonant to the exciton wavelength. If we look at the physics behind, this is pretty similar to the traditional single resonance or double resonance cavities for the nonlinear optics. But here we don't use the cavity, but we use the bonded electron and hole pairs with the exciton resonance. Just recently, we also demonstrated a new way to increase the nonlinear response by the energy transfer. So this is the devices fabricated by the Kaihui's group in China. He coated a thin layer of the quantum dot on the monolayer MOS2. Because of the quantum dot, they have the central symmetric structure. We don't observe the second Hamar generation. But however, when we put the quantum dot on the MOS2, then we found that the second Hamar generation has been enhanced by more than 1,000 times. So this is really amazing. So to cut the story short, the physics behind this enhancement is because of the quantum dot has a very strong multi-photon absorption coefficient. When this quantum dot absorbs the light, they can quickly transfer the energy to the MOS2 for the very high efficient second Hamar generation. We also found the energy transfer process is quite universal. It works also with the third Hamar generation inside the graphene, and also even for the second Hamar generation instead of the fourth Hamar generation instead of the boron nitride. Another unconventional way we are working on is to use the excited carrier states. So here is our experimental setup. So what we did here is that before we are measuring the second Hamar generation of the state laser, before we measure that second Hamar generation, we pump the materials with another control light. And then we check the second Hamar generation of the state as a function of the delay between the state light and the control light. Our results show that the second Hamar generation intensity increases significantly with the time delay. This indicates a very strong enhancement with the excited carriers created by the control light. This figure gives some little bit more information. The black curve shows the second Hamar generation without the control light, and with the control light, you can see the second Hamar generation increases significantly. We attribute the enhancement effect to the excited excitonic state created by the control light. If we change the theta wavelength, we find even more interesting results. For a very broad spectrum range, we can find the enhancement of second Hamar generation for some spectral regimes. And we also find some suppression regimes for some wavelengths. Then if we plot the modulation at a fixed wavelength around 1 picoseconds, and then we could get this modulation depth as a function of the different second Hamar generation wavelengths. Here we could easily correlate the peaks at the different enhancement state and also the suppression regimes with the different excitonic state inside of the MOS2. So the results here to show that this time-resolved second Hamar generation measurement not only provide an effective way to enhance the second Hamar generation, but also provide a very useful method to probe the exotonic states inside of the MS2 inside of the 2D materials. We also did time resolved third Hamoir generation. We also found some similar results, and we found that the time resolved third Hamoir generation also can be very useful method to probe the carrier dynamics. The results is showing here. If you look at the time response, you can clearly see that. So when we pump, when we incident the light at 400 nanometer instead of the MS2, we can clearly see that how the carriers relaxed from very high energy state to the very low energy state. So this is something extremely interesting. For future perspectives, so what we are planning to do is at the moment, even a lot of these nanomaterials have been already used for nonlinear optics. Here, due to the time limits, I mainly introduce you our work about the TMDs, but I believe in the near future, the different new nanomaterials and their combined structures will be studied for the nonlinear response. For example, here, this is an example of our recent published paper. We found that one-dimensional van der Waals semiconductor red phosphorus have a very large Chi3 response, much stronger if you compare to the with monolayer MS2 and also other well-known Chi3 materials. As I mentioned, the nonlinear materials has this very weak conversion efficiency, very weak nonlinear conversion efficiency because of the very thin, very short light-matter interaction lengths. So for future, the new fabrication method and also integration structures will be needed to improve the light-matter interaction. This is also provide a lot of new opportunities, for example, fully fiber integrated devices, as I discussed, and also the different on-chip devices. At the moment, it's very interesting to change, to look at the optical properties and also electrical properties of the 2D materials with the different degrees of the freedom. For example, valley and also interlayer combinations, magic angles by twisting, and also doping, and also defect engineering. This also provide very unique advantages to tuning the properties of the 2D materials. On the other hand, this is also provided unique advantages for us, for the nonlinear optic guys, to support the relevant research directions. For example, as I mentioned, the nonlinear optics can be used to measure the angles, to measure the doping, and also could be able to look at the carrier and also electrical dynamics. So this is also providing huge opportunities for the future research. Again, so the field of the 2D materials-based nonlinear optics is very, very young. Even at the moment, it has gained a lot of interesting because of the huge potential for the large number of the technological applications. For example, people are working very hard try to demonstrate the 2D materials based on chip devices, for example, for the terahertz generation and also for the on-chip quantum photonic devices. So I'm expecting for the future, the study of the 2D materials based nonlinear optics will need a lot of the new opportunities for the photonics applications. In the end, I would like to thank all of my group members for their excellent work. This is our very recent new group photos. And here we also welcome the highly motivated PhD students and postdocs to join our group. These slides briefly introduce my group activities. I already mentioned the work about the nonlinear optics. We also have been working on the lasers and also the quantum physics and the applications for the different photonics and electrical applications. If you are really looking forward some collaborations with the 2D materials for different photonic applications, please contact me. We are really looking forward to collaboration with you. This is one of the most important slides. I would also like to thank the great collaborators. Without them, nothing is impossible here. We also thank the funding agency for the support. Before I finish my talk, I also give a small job advertisement. So if you know somebody from your group or want to, feel Brazil is too hot for you and are very interested to move to the Finland, please contact me. I thank you for your attention, and now I'm ready to take any questions. Thank you.
Thank you for the presentation. It's a lot of results to show. We have some questions in the Q&A.
Yes.
Yes, about your physical review B. Yes, the question is from Pilar Viana. It's a PhD student. Some substrate different TMD. Congratulations. Time-consuming sample preparation, maybe the one challenge. How to quantify the second order nonlinear effect contribution and the PL resonant contribution for the annual SE2 case?
So in our case, we tried to use different strategies to remove the photoluminescence resonance. So one easy way to do that is if you look at the measurement I mentioned, the second Hamar generation, if we use a polarized second Hamar generation, the generated light is always position dependent. But for the photoluminescence resonance, so the PL emission is always doesn't have any polarization preference. This is because of this is a spontaneous process. So with this way, we could easily remove the contributions from the photoluminescence process.
Okay. The next one is from Henrique Rosa, is a professor here in the Mackenzie University. He asked, we realized that 2D materials optical properties like harmonic generation, PL wide, the photoluminescence, saturation absorber, have some dependence on material synthesis routes, crystal quality, chemical residues. How do you quantify or treat these extrinsic factors in your experiments?
So thanks for this question, which is really nice, because at the moment I have to agree that we don't have a huge control in terms of the lot of these extrinsic factors. For example, even with the mechanics exfoliated flakes, we always can find the defects. So for example, with mechanics exfoliation, we tried to look at the TM, we still could find a lot of this lot of defects on the surface. So this is something we cannot easily to control, but what we can get the conclusion is if we fabricated with the devices like what I mentioned, with different flakes, use a similar method. So in this way, we could compare the method in a pretty fair way to exclude all those these extrinsic factors in the measurement. But again, I also want to highlight that. So at the moment, there's a huge interest in, for example, to control by these extrinsic factors, for example, to change the crystal qualities, to change the chemical residues. Even, for example, you can put some different, with a different substrate and try to look at how those factors will affect the nonlinear response. This is also at the moment, this is a very hot topic for the nonlinear optics society.
Okay. Then the next question is from Danilo Nagaoka. He's a PhD student from the university. I think he's talking about the PCF, the photonic crystal fibers, the channels filled with 2D materials, graphene or MOS2. What are they made of? There are any required pre-treatments to improve the affinity of the 2D materials and these microchannels?
Those samples are fabricated by our Chinese collaborator. As far as I know, they don't have a very significant pre-treatment. What they did is they purchased this commercialized photonic crystal fibers from company. Then they use different methods to CVD methods, chemical vapor deposition method, to deposit the 2D material inside of the photonic crystal fiber. For example, for the graphene, they use a different gas phase chemical vapor deposition method. But when you deposit the MOS2, they found that it's not very efficient. So what they did is they dip the photonic crystal fiber inside of the precursor solution. Then these precursors will go inside of the photonic crystal fiber, and then they put the photonic crystal fiber inside of the CVD furnace to do this sulfurization to get this monolayer MOS2 inside of the photonic crystal fiber.
Cristiano Toro, if you want to ask, it's okay.
Yes, I have a question. Well, first of all, actually, I have two questions. Zhipei, very, very interesting presentation. Thank you very much. I'm talking to my group while we listen to you, and I mean, it's very interesting. So I have two questions. The first one is regarding the work with quantum dots. What is it? The pump needs to be resonant with the quantum dot. Is this right?
Yes, you're correct.
It's,
so
it's the pump that is
resonant. Be resonance to the multi-absorption resonance of the quantum dot.
Okay. Okay.
So we also checked that during the wavelengths, when the incident wavelength is off resonance, we don't see huge effects.
Right. Right. The other question is regarding the very curious observation that second harmonic generation in MOS2 is weaker than it should be, and I find it interesting that you say that it's still not fully understood, because I remember something that you mentioned in one of your first papers that made sense to me, which is that the bands, even though the material is not centrosymmetric, the bands involved in the transition, the main bands are almost centrosymmetric. Does this theory doesn't hold, or does it have any problems that cannot be solved?
Yes, so we're working with Professor Javier Abajo from ICFU in Spain. So what he did is that he extracted all the band structures from 4 different materials and tried to calculate this nonlinear response with the different, this force principle, whatever this method. But however, for the MOS2, the difference between the theoretical results and experimental results is much, much larger than other 3. So this is still most likely, I think we agree with you, most likely because of this subband structure. But we haven't been able to fully confirm this, link this with experimental result and theoretical results.
Right, right. Thank you.
Okay. Tora, do you want to?
Yes. Okay. Thank you. Yeah. Hi. Congratulations, Zhipei, for your excellent talk, and
thank you.
From this overview of your work in many fields. It's very inspiring for all of us here. And my question, I have a few questions. One of them is related to the integration. Are you guys doing something related to integrate these devices to optical communication system or something like that?
Yes. So we have been trying, for example, as I mentioned to you, we integrate the 2D metal on top of the silicon nitride devices. And now we also tested the devices at the telecom wavelengths. So in principle, for example, what we expected is this full wave mixing can be significantly enhanced, for example, for the data exchanging, for the optical switching, for the very high speed. So this is something also we want to try.
You haven't done yet this.
We tried with the 1550, but the results are not showing here. We didn't get significant good results compared to the results we get at 800 at the moment. Yeah. So.
But okay, but if you think about the integration, one problem that comes out is scalability.
Yes.
And most of the material that they're using, that you are using also in our group, is comes from bulk material. You have to scratch and things like that. So this is not feasible in order to put this in a scalable way. Have you thought about this?
Yes, so you're right. So if we consider at the moment the current state of the art measurements are using this, for example, small piece of mechanics phonation devices, or even you cut a few pieces from the CVD samples. So this is not most likely this will be not practical for the applications. So the future, I think I personally think for the future devices, you must to combine this integration with some large scale fabrication technology. As I mentioned here, for example, with a large scale chemical vapor deposition method. For example, we also have demonstrated, as I showed you already. So for example, with large scale fabrication, people nowadays can fabricate, put the graphene and also the monolayer material inside of the photonic crystal fiber up to half a meter. In this way, for example, for applications, you don't need a very large, very long fiber. For example, for satellite absorbers. So you can just cut this very long piece into very small pieces. You could be able to get a lot of products. And with this graphene device as well. So for example, these devices I didn't show you actually. So this device is a fully fiber integrated devices. So this is this 1,400 devices is a fully fiber integrated devices. So this devices, so it's a fully fiber integrated, and we could be able to, fabricate more than 1,000 devices one wafer, and we put this shape because we can directly put the fiber here. So this is a no problem to get the large scale, but you're right. We have a lot of things to be addressed for fully, to push the applications of the 2D materials for the applications. Yeah, one of the major things I think is how to find the best applications. I don't think this graphene or 2D materials will easily replace the current silicon technology. So the best way for the 2D materials is to find the right applications which can be complementary to the current photonics technologies. So this is my personal view.
Okay, yeah, I totally agree with you. I think gallium arsenide also did didn't manage to overcome the silicon technology. So graphene has, let's say, a bigger problem than gallium arsenide for this application. One of them is the gap in the, the integration is, I think, easier, but we have more fundamental problems, I think. But my other question is related to your view from the quantum physics. What's your goal in quantum physics?
So at the moment, a small subgroup inside of my big group is working on the quantum physics. Yeah. So we have a different things to working on. So we want to go to the low temperature to look at this exciton dynamics. For example, now we found something very interesting. For example, to be able to use a string to tuning or to change the properties of the excitons and also light emission. We want to go a little bit more deeper in that direction. Another direction, what we are working on, which is we are collaborating with other peoples. We are trying to look at to create the single defects inside of the 2D materials. We try to get the single photon emission from these 2D materials. So this is related to the quantum photonics. A lot of opportunities here. And I would also like to highlight that. So if we don't talk about the application of the 2D materials, for physics behind the 2D materials will be much, much more interesting actually for at the moment.
Okay. Okay. You said that single photon emission. Yeah, not easy, but I like the idea. I think we have to discuss more about that later. Okay. And so thank you very much for.
Sorry, there is a last question that I see here about the theory. Gina is a master student, and she asked about the mathematics and the theory. Can you comment a little bit about the theory? What do you recommend about the theory about 2D materials? You said about the here about the quantum, but can you comment about it?
Yes, so this is a very good question. So at the moment, for example, as I mentioned, there are too many 2D materials. Even for example, in my group, if I have 1,000 students, each of them working on one materials, we wouldn't be able to, to do all the measurements. So in this way, the future research, we really need to work close together with the theoretical people to use the theoretical way to look at which materials will be useful for the different properties. But then if you consider the symmetric, so you can easily use a symmetric definition of the different materials to easily find some useful materials for different applications. Just to give you an example, for example, if you look at the symmetric of the central symmetric structure of the different 2D materials, if you found that you have a certain symmetric structure for 1D or 2D materials, you know that those nanomaterials were not interesting for second Hammond generation. So this will be the easy way to do that. And also another interesting research direction is people at the moment are trying to use the machine learning or use the artificial intelligence or whatever, this advanced computer science to fasten this mathematical understanding about all the different properties of the different nanomaterials, including 2D, 1D, and also zero dimensions. So at the moment, this is also some new opportunities for the theoretical people as well. So, but anyway, I think this will provide a huge opportunity for theoretical people and also to work with experimental people to closely working together for a lot of new opportunities.
Okay, thank you. Thank you so much for all the presentation and the answer. It's a pleasure to receive you here. Thank you so much.
Thank you. It's my great honor. So hopefully to meet you in person, maybe
Yeah,
next
I hope
August.
so.
Yeah.
Yes.
Thank you very much, Zhipei.
Thank
Yes.
you.
Thank you.
Thank you very much, Zhipei. And I'm sure that we are going to do some work together. Okay, our groups have similar, or in many cases the same interest, and for me it's really natural that we collaborate very soon.
I'll be very happy. I'll be very happy. My great honor to work with all of you.
Okay. Okay. Thank you very much.
Thank you.
Thank
Bye-bye.
you. Bye-bye.
Bye-bye.
Bom, é isso, pessoal. Obrigado pela presença de todos.